Hello, today I am going to talk about Traveler, our designed performance visualization tool for task parallel traces. Understanding the behavior of software in execution is a key step in identifying and fixing performance issues to achieve good execution performance. This is especially important in high performance computing context where even minor performance tweaks can translate into larger savings of computational resources. Having a good execution performance means how to achieve the shortest time to solution and efficiency in hardware resource usage. This allows to run more sophisticated computations with minimized cost. Asynchronous task parallel programming is a popular programming paradigm for achieving good performance. So let's talk about our data and domain by introducing what a task parallel program is. Consider a program running a function 6 times, and we have 3 available networked CPUs for execution. If we call a unit of execution a task, this code snippet will produce 6 tasks while iterating inside this for loop. These 6 tasks could be distributed into 3 groups like this, and each group of tasks can be executed parallelly in each of these CPUs. This enables increased resource utilization by dividing work among many resources executing in parallel. Since in this programming paradigm, tasks can be moved around between resources and idle resources can be allocated to potentially different types of tasks. This allows efficient resource utilization and faster program execution. We could leverage visualization to conduct performance analysis of task parallel programs. To do that, execution traces of task parallel program is collected. Execution trace is a chronological record of per resource events captured during the program execution. A typical execution trace data includes start time and finish time of a task at a specific computing location, in this case CPUs. However, interactive trace visualization is very difficult due to issues of data size and complexity of their meaning. Let's take a closer look into these problems. We can visualize the parallel tasks using a Gantt chart where x-axis represents time and y-axis represents each computing resource location. Here you can see each bar represents each task execution location, its start time and end time. For longer running programs using higher number of computing locations could overcrowd the visual interface. It also complicates the relation between events and their probable cause. To express the overall overview of the whole execution, we could visualize the utilization, which is the number of parallel resources active or not being idle throughout the execution. The utilization view, which is presented here at the top, shows the total utilization over time using an area chart. The height of the area chart at any pixel is the total amount of resource activity in that time span divided by the total time span. It is noticeable that at the beginning, no resource is being utilized. In the middle portion, at most one CPU is being used, and in the later half of the total execution, all 16 CPUs are being utilized. The utilization view gives a good overview of the execution and how resources are being utilized over time, while the Gantt view gives specific details about each task. The scale difference between the entire execution length of the trace represented by the utilization view and individual intervals shown in the Gantt view is vast. The scale of individual events is orders of magnitude smaller than the length of the total execution length. Also, identifying behaviors of the program or system from the trace events that lead to them requires navigating a large space where details matter, such as relationship and dependencies between tasks in varying scale. It requires multiple back and forth interactions between the utilization view and Gantt view to explore the trace data and identify probable tasks which contribute into the performance bottlenecks or add overhead into the overall execution. So it becomes harder to navigate through tasks and dependencies in between them in varying scale. So to understand the dependencies between the tasks, let's consider these code snippets. Here, if a function do A calls another function do B, subsequently that function calls three other functions C, D, and E. We can visualize this dependency relationship using Gantt chart like this. Here, B is the parent task and C, D, and E are the children tasks of B. We presented their relationship using yellow lines here. This way of visualizing dependencies could overclutter the visual interface. It also becomes more messy and harder to follow along the parent or child tasks. We can use node link diagram to represent the task dependencies. If you notice in the bottom right, each individual task is being represented using a single node, and the edges between them indicate their dependencies. We call this dependency tree. Here, you can see that same dependencies are being visualized using a Gantt chart in the bottom left and dependency tree in the bottom right. Now, we can also aggregate the bars in the Gantt chart by the same subtree rooted at a node. Our developed visualization tool helps to bridge the abstraction between overview and detail by aggregating tasks by their tree relationships. So let's take a closer look at a small example. In the dependency tree in the left, we can select a node like this run helper. Here, the dependency tree, however, shows the aggregated task dependencies. There are actually multiple instances of run helper in the Gantt view. We can also consider the subtree of tasks generated from run helper and then use color to show the different subtrees in the Gantt. Finally, we can also represent these meaningful groups of tasks, this iteration of run helper, as their own span in an aggregated Gantt view. Here for the first iteration and here for the second one. These are now aggregated enough. We can also show how utilization is apportioned among them. Note that the aggregated Gantt view at the bottom right, the rows here represent how many instances of run helper are being overlapping in this specific time span. Once we do this, we can now navigate the dependency tree to find places of interest. In this example, these two nodes have little impact on the overall execution. We can collapse these two nodes to narrow down our exploration. Now we find the task having highest impact which is associated with this selected node. This can be verified from the utilization view at the top left, which is showing large yellow area for this selected node. Also, we can see different instances of this node in the aggregated Gantt view in the bottom left. Furthermore, each individual children tasks can be identified with matching purple shades in the Gantt view. Now, if we follow along the children nodes, we can track down how this task is progressed. Eventually, when we reach the leaf node, it shows the individual detail. Notice that in the aggregated Gantt view and Gantt view look similar, since the leaf node doesn't have any dependent children. Therefore, there is no aggregation happening. In this way, Traveler helps to explore more of the dependencies that matter to us most and facilitate the navigation through tasks and dependencies between them in varying scale. We can also combine with other views to track down interesting tasks. This helps to further narrow down the exploration. We present the design of Traveler, a highly linked multi-view coordinated visualization for visual exploration of task parallel execution traces. We showed how a dependency tree and aggregated Gantt view help to manage and interpret the vast scale differences in the trace data and provide a way to understand the relationship between the tasks which have been scheduled asynchronously. Thank you all for attending my talk, and I am happy to take any questions.